Okay, hello everybody, here is Jaakko. Some of you asked for information about the wire EDM that I have made and about the electronics regarding the machine. The machine itself is mechanically just like CNC milling machine, 2-axis CNC milling machine. So nothing special in that regards, but the electronics for the actual EDM part are a little different, and interfacing this with the controller requires some knowledge. And I'll try to be as thorough as possible with this video, so if you have any questions, please ask them directly on my email. I'll have the email address below this video, so you can send all your questions there. Okay, so let's start. The very basics of the machine. We have a controller here, Arduino Mega. Connected to it is an LCD display, a keypad. These are all the user interface systems, and also one potentiometer for setting the cap voltage. On the motor control side, we have two stepper drivers driving the X and Y stepper motors, and there is one stepper motor power supply, and directly connected to these motors are 5mm pitch ball screws, and I'm driving these stepper motors with something like 5000 microsteps per revolution, so I know that when I ask for one step it goes 1,000th of a millimeter movement, and that makes it easy to code. The actual accuracy is of course not so high, but it makes things a lot easier. Next up is a wire puller. This is also controlling a motor. I'm driving it with a pulse width modulated signal, and basically I can set the speed either with a potentiometer or in the code itself to get proper speed for the wire. Too slow it burns through, and too fast it just wastes wire. That's nothing special. It's an off-the-shelf controller for a DC motor. I have something like 50 watt powered DC motor with a small gearbox on it, and I'm able to achieve something in the order of 15 meters per minute, which is quite much fast. Too fast actually. The usual is around 1 meter or 2 meters per minute wire speed. Then there's a whole bunch of relays. I actually have one relay board, but I'm only using at the moment 3. There's one relay to control filtering pump, one relay to control flushing pump, and one relay to control the deionizing resin pump. And I drew a small diagram of the machine's water system to illustrate what all these 3 pumps will do. And in the water system I have, here is my work tank, the place where all the magic happens, and below that I have one large container for dirty water, that is the used water that is coming from the work tank. From there I have an overflow pipe to the clean tank, which contains clean water. And I'm sorry, there's actually there's a mistake. This overflow pipe should go this way, and this pump filter assembly here should pump from dirty water tank to the clean tank, not the other way around. So in normal operation the filtering pump is always running whenever there is any other pump activity or when the code is running. This makes sure that there's always clean water available for any operation, and the overflow pipe makes it so that the level in the clean water tank never rises above the container, and anything unspent just overflows to the dirty water tank for recirculation. Then in the dirty water tank I have another pump connected to it that pumps through a small filter assembly that is filled with deionizing resin, small pellets that will remove the electric conductivity from the water. And it basically tries to maintain the electric properties of the water all the time. Now, the better idea would be to include this into the clean water tank. And yet again, this is actually a drawing error. This was late at night when I was drawing this from my memory, so excuse me. But it doesn't do anything other than circulate water through the resin only when needed. Connected to the Arduino is a small EC meter, electric conductivity meter, that is constantly looking at the clean water tank to see if the water is properly maintained with the conductance, and it should be in the range of say 10 to 50 microsiemens conductivity. My meter can go as below as 11, so basically when I get a flat out reading I'm good. Below this is not very good. It doesn't conduct basically at all, which is too bad. And above this means that there's too much leakage current going on, and almost all the spark power goes through the water and not to the workpiece. Then there's the flushing pump. This is actually drawn correctly. It pumps clean water through two nozzles, the upper and lower nozzles, which are just after the wire guides. And this is to provide flushing to get all the cut debris and small swarf away from the cut area and to keep it clean. And as said, there is an overflow in the work tank, so the cut piece is always submerged underwater. This is to reduce any thermal stresses and also to keep all the debris in the water and not flowing into the air. And it also stabilizes the sparking process very much. About the filtering pump here, I actually included one pressure gauge to show it's actually differential pressure gauge that shows how clogged the filters are. I'm using a basic household drinking water filters, the cartridge type filters. They are pretty cheap, couple of euros per cartridge, but they tend to last only for a few hours. I would say 10 or 20 hours of cutting. Okay, then the part where actually I have got a lot of questions about is about the actual EDM part. What I have here is a power supply for all the logics in the unit. 5 volts DC regulated, nothing special. It's feeding the Arduino and it's sharing a ground. This is ground potential to have less problems and less electric shocks from the machine. It's sharing the ground potential with the actual EDM power supply, which is pictured here. This is providing 100 volts DC voltage, and in my machine it is supplying about 1 amp of current max. As I have said, it is a prototype machine, but if you want to go so-called full power, I would say 5 amps max. This is nothing but a toroidal transformer, bridge rectifier and a huge capacitor to smooth it out a little. Why 5 amps? Because the usual wire that is used is 0.25 millimeters in diameter, so that just doesn't work with much more power than that. The positive end of this supply is connected to the ground. The negative lead goes through a power resistor, and the power resistor sets the absolute maximum current that is being drawn from the supply when short circuit occurs, meaning that when the wire touches workpiece. And this can happen during cutting or in accident, so this has to withstand all the power that is coming from here, though not constantly. This would mean 500 watt power resistor, which is quite huge and expensive, so it's easier to make from smaller resistors in parallel, and it can be something like 2/3 of the power rating required, because the power dispensed as heat here is so intermittent. I would suggest a huge heatsink and a cooling fan for the resistors. In my own machine, because I have 1 amp max from the power supply, I have a 100 ohm resistor array here, which can dispense something like 70 watts of power, and it's enough, it doesn't burn. After this is a capacitor. This is a polyethylene cap, so it's non-polarized, and in my machine it is 0.47 microfarads in size, with 250 volts maximum. This is the basics of the power supply. It's basic RC circuit, so it has a resistor and capacitor, and these form an oscillator basically. And depending on these values depends the frequency of the oscillation. I would say that anything for this kind of machine should be between 10 and whatever what you want is the maximum frequency in kilohertz. But I would say 10 kilohertz is the absolute minimum, because anything lower means usually that it isn't sparking, it's actually making an arc which just burns the wire, burns the workpiece, and doesn't do anything good. As I said, in my own machine I have 100 ohm resistor here and 47 microfarad cap here. It works. I haven't kind of calculated what the actual frequency is, as it depends on a lot of more things, but it works. I actually originally had several capacitors in parallel with switches on them, as well as with the resistor, but this has been proven to work, so I'm going with that. If you increase power, you of course have to change the resistor, and then you have to change the capacitor. It's a kind of try it out. If it doesn't work, change it. But be reasonable. This requires only small changes usually, and the size is in the microfarad range. Then there is the negative side that connects to the wire. There's an actual small part in the machine that conducts the electricity to the wire via a carbide insert. I basically have the wire going straight through the wire guides, and there's a small around old end mill, actually a solid carbide end mill piece, 6mm diameter, pushed in through the wire guide system, so that it kind of rests against the wire before it goes through the wire guide. This nice box here represents the wire guide. So this conducts the electricity. There's a electric wire connected to this carbide piece. Otherwise the wire is insulated from the machine itself. There's also conductors on the upper wire guide and lower wire guide. So on the below wire guide there's a actual contact is made here, and then the wire goes away. But something like that. Explained easily. The earth potential for the machine, and in the same time the EDM power supply positive side, is connected to the workpiece. And this means basically the table of the machine is connected to earth. Then there's the very important thing of how do you measure what is the potential between the wire and the workpiece when it is working. Because in essence you will have this is the ideal situation. You have a, let's make a small graph. So here we have time, and here we have voltage. Let's say that's our 100 volts maximum. And when the wire comes close to the workpiece but is not touching and not close enough for spark to happen, the gap voltage is at the maximum. As soon as a spark hits, the voltage drops to a certain value, and the machine detects this drop or lowering in voltage and stops the machine from moving. And of course, when it stops moving, the gap voltage remains at some level. The machine tries to keep some level preset by the potentiometer, and I would say something in the order of 60 or 80 volts. This is the usual I've been working with, and basically because it tries to keep it there, it's constantly changing a little, and then the spark should end, meaning the voltage goes to zero. Sorry, it doesn't go to zero, it goes up again. But if it comes in contact with the workpiece or there is some crap in the gap, then it goes to zero, which is shortcut, and the machine should back out from the cut to clear it, or just wait a while to see if it clears. But in normal operation it just continues to spark a little, goes back up, sparks a little, goes back up. So this is the ideal thing, but what you would actually see is something very, very, very different, especially for RC oscillator, as it's free oscillating system and you don't have much control other than for the frequency. So what you are trying to measure is this voltage, and trying to keep it there while working. I didn't want to build anything too fancy, so I just made a system that measures the average voltage, meaning it's basically trying to measure this voltage here. Now it doesn't matter that much what you're measuring in this case. It's a hobby machine, it's not for production, blah blah blah, but it gets the job done, and it's actually fairly good representation of the actual voltage. And I measure it by bringing the voltage from the wire through a resistor divider and feeding it to the Arduino via analog input. I have two diodes here to get me, these are extra fast or ultra fast diodes to give some extra protection for the Arduino input. There is some diodes in the input already, but just in case, never hurts and doesn't cost anything. There's also a small capacitor, 220 nanofarads in size, to smooth out the voltage reading, so it keeps it a little bit more constant than what it would otherwise be. This is completely experimental value. This doesn't have any calculations behind it. I just took one from a scrap pile and tested. It worked, so I haven't changed it. The resistor divider has one diode in series with it. This is just to provide that the actual pulse that comes from the wire is of negative voltage, because of the sparking the voltage actually fluctuates between positive and negative a little bit. So this is to protect the system and to provide only with the actual readings and not the overshoots to the other direction. The thing here that it was at first difficult for me, and what I finally figured out was how do you measure a negative voltage when your measurement equipment is on the positive side. But I just realized that I can make an inverted measurement with resistor divider and I get the perfect readings for it. This point here is what I'm feeding to the Arduino, is between 0 and 5 volts. Now this point here, the wire, is between 0 it's between -100 and 0 volts. So here we have 0 to 5 volts available, which is positive. So how do I get this? Well, the thing is that I can actually just feed 5 volts and try to pull it down with this. With proper resistor values, I can get it so that when the wire is at 0 volts, meaning at ground potential, I get in here almost full 5 volts. But when this goes more negative, meaning it tries to pull the voltage from this point down, when it goes to 100, this point goes to 0 volts. So the resistor values have to be such that with -100 volts on this wire, this is at 0, and with nothing on this wire, meaning 0, this has to be 5 volts or very, very close to it. So my solution was to put a 100k resistor and 10k trim pot on this one, so I could just adjust this point to be between these values. Now the Arduino input doesn't handle negative inputs basically at all, but it can handle a little bit positive. So if I put this so that it remains at 0 minimum with the 100 volt negative input on this lead, I'm safe, because this can't climb higher than 5 volts because it's limited by the logic supply, which is 5 volts. If you would like to make this more sophisticated or more protected, you would have to have this measurement system separate from the Arduino, basically having an optocoupler between this wire and just feeding a digital signal to the Arduino telling, can you go forward or do you have to wait? Because the Arduino inside the code is just comparing this reading and the reading from a potentiometer and seeing if they match, or if this is higher or the same as the set value, it will continue executing the code and stepping the motors until this value goes too low, in which case it stops and waits. And in the event that the value goes too low or goes to zero, meaning it's in a short circuit, then in that case the Arduino tries to back out from the cut. But that doesn't have to do anything with the control electronics, it's just a matter of coding. But that's about it. That's the very at least I tried to make it very detailed explanation of the electronics I have in my machine. I'm not sure if I missed anything, but this is the thing I've been working with for the past year or two, and it's still a prototype, but it works, and people have seen the parts that I have made with it. The rest is just mechanics, and I can make separate videos of the mechanical parts if people would like to see them. And I can supply the code for the Arduino, but this is a huge but, because I have made so much different things with it. It's a whole mess. The whole code is a mess. So it's pretty much commented well, but it's relying on certain things, and it's just it's basically it's expecting certain things to be there regarding the parts, the values, everything. So it gives you an idea of what is happening, but in essence it's in the heart there's a G-code interpreter that I basically ripped off from a project called GRBL. I think it can be found from GitHub or something like that. Google. And on top of that, I just made my own stepper motor control, so it gives step and direction signals to the motors, and then a main loop basically which is waiting for the voltage values to be correct before advancing another step. After all that, there's also kind of in the background is control for all the not so important stuff that's not time sensitive, which is the wire puller, the relays, EC meter, reading the keypad, displaying stuff on the display. They're just slapped on user interface to get things going. And and also I have a micro SD card reader connected to the Arduino also. This is so that I can upload a G-code file from a computer to the Arduino, and it saves to the micro SD card on the fly, and then executes all the code from the micro SD card instead of trying to get the file over serial connection from the computer, which is kind of unreliable and requires the computer to be on at all times. So that's about it. If you have any questions, please feel to shoot me an email. I'll try to answer it when I have time. Usually I have time. And also, if you have any comments or suggestions or anything, please share them. And if you would like to see more videos of the actual machine and the mechanical parts, please tell me so I know that there's interest in seeing that kind of stuff. But for now, this is what you get and this is what I can give. So thank you for watching me.